Yeah, good morning, dear students. So this is Dr. Vijaya Babu. So today we'll try to discuss about one of the very important law, that is Kirchoff's voltage law. Usually to solve the electrical circuit problems or current electricity problems, okay. So most of the times we use it to apply two important basic laws. They are Kirchoff's voltage law and Kirchoff's current law. So we'll try to discuss something in deep insights about this Kirchoff's voltage law today in this lecture. And in the next lecture, we'll try to continue with the Kirchoff's current law. So coming to the Kirchhoff's voltage law, I'll try to divide this Kirchhoff's voltage law into two basic laws. Once again, I'll try to call them as KVL1 and this is KVL2. I can divide this into two laws once again, two sub laws, KVL1 and KVL2. So how I can explain this KVL1? So Kirchhoff's voltage law 1. So let us consider the nodes. Let us consider this is a node with A, this is a node A, and this is node B, this is node C, and this is node D. Similarly, this is, let us consider this is node E, and this is, I'll try to consider only one node E, and this is D. So let us try to assume some potentials already exist at these different nodes. That means potential at node A, so let us consider it as something 8 volts. The potential at node B, I'll try to consider it as 3 volts. Potential at C, consider it as 5 volts. Potential at D, consider it as 2 volts. Potential at E, so let us consider it as something 4 volts. Okay, so now what this Kirchhoff's voltage law 1 is saying. So simply see here. I'll try. The target is to calculate the potential difference between points A and D in this particular example. That means the potential difference between A and D, that is the calculation of VAD. So this is very, very important what I want. So I'll try to calculate the potential difference between the points VAD. So VAD, which path you can consider for the calculation? You can consider the path from A, B, C, D, something like this. V, A, B, C, D, or else another approach to calculate it, VAD, you can calculate like VAED path. That means if you clearly observe here, you can consider a path something like this through BC points, or a path something like this through E point. So this is how you can calculate the potential difference between the points A and D. Then I'll try to go ahead. So which is equal to, what is this VABCD is nothing but VAB plus VBC plus VCD. This is how you can write VAB plus VBC plus VCD is equal to this. So what is this VAB? So VAB is nothing but VB minus VA. You know the well-known formula for the voltage between A and B. It is potential at B minus potential at A. Similarly, VC minus VB plus VD minus VC. Okay, I'm going further. Substitute the potential at B, that is 3 minus 8 plus 5 minus 3 plus 2 minus 5. Okay, so with this logic, simply the answer what you're getting it as 2 minus 8, finally remaining will be cancelled now. So is equal to 2 minus 8 is equal to minus 6 volts. So this is one method you can apply Kirchhoff's voltage law 1 to calculate the potential difference between the 2 points A and D. So another approach is what I have given here, VAD. That means VAE plus VED. which is equal to, so what is this VAE? VE minus VA, VE minus VA plus VD minus VA. So that is VE minus VA 4 minus 8 plus VD minus VE 2 minus 4. Okay, if you try to calculate this, so how much you're getting? Once again, 2 minus 8, which is equal to minus 6. Minus 6 volts. Okay, or else another simple approach, VAD is directly VD minus VA. Directly you can write it now. So VD minus VA, how can you write this answer? VD as 2 volts minus VA as 8 volts. So 2 minus 8, it is minus 6 volts. So unfortunately the answer for all these three different approaches, what I got is same. So that is minus 6 volts. That is the potential difference between the 2 points A and D. But the methods what I have followed is different methods. One, I have followed in this path VA through the points B and C, I reach D, or else in the second case, I approach this one. So if I call it as 1, if I call it as 2, and if I call it as 3, so this is the path 1, this is path 2. So what about path 3 then? So path 3 is simply directly taking this path, that is 3. So that means what? Now I will try to write the definition for KVL1. So what is the definition for KVL1? So definition is very simple. The potential difference between any 2 points is independent of path taken. Okay, it is independent of path taken. That means if you follow the points A, B, C, D, something like this, or else if you follow the point something like this, A, E, D, something like this, or else if you take direct the two extreme points, that is A and D, so directly you'll be getting the same potential difference between the 2 points. So this is what the KVL1 law says. Now we'll try to go ahead with the KVL2. So what is this KVL2 says? Actually, usually we will call this as the KVL law, that is KVL2. Usually you call it as KVL, Kirchoff's voltage law. So the law says something like this. The algebraic sum of voltages in a loop is equal to 0. So the algebraic sum of voltages in a loop, that is equal to 0. That's what KVL says, or KVL2 says, or usually this is the final law of KVL. Algebraic sum of voltage in a loop is equal to 0. So how can you get back this? So with the same example what I have discussed for KVL1, the same example I want to follow for KVL2. So if I try to go ahead for KVL2, the same example, I will try to calculate. You need to make the loop, means wherever you are starting, once again you should come back to the same point once again. Then only we can understand that we have completed that loop. So right, so that means I start with A point, VA, E, D, C, B, A. Okay, so this is VAE, D, C, B, A. This is what we have to prove is exactly equal to 0. So this is the meaning of algebraic sum of voltages in a loop is 0. How it is happening? So understand this clearly. VAE plus VED plus VDC plus VCB plus VBA is equal to 0. How we prove this? So let us go ahead. This is how you can write VE minus VA plus VD minus VE plus VC minus VD plus VB minus VC plus VA minus VB is equal to 0. So this is the thing what we have to prove. Okay, I'll try to substitute the potential values at individual distinct nodes. Now, VE, so what is the voltage? So 4 minus, what is A? 8. 4 minus 8 plus VD minus VE, that is 2 minus 4 plus VC minus VD, 5 minus 2 plus VB minus VC, 3 minus 5 plus, then finally VA minus VB, that is 8 minus 3, which is equal to 0. Okay, is it happening 0? So let us check. So I'll try to cancel this with the blue color now. So cancel the terms. So minus 8 plus 8 gone, plus 3 minus 3 gone, 5 minus 5 gone, 2 minus 2 gone, 4 minus 4 gone. So finally 0 is equal to 0, that is satisfied. Okay, so in the same way, or else instead of substituting the potential points, go with the potential at different nodes. So VE, you can cancel with this minus VE. In the same way, minus VA, you can cancel with plus VA. In the same way, VD, you can cancel with minus VD. And VC, you cancel with minus VC. And VB, you cancel with minus VB. So unfortunately, here also the same thing is happened now. So in both the cases, I think we got the algebraic sum of voltages throughout this loop is exactly 0. It is not the loop you can take this loop, or else in the same method, I can, if I start with a point D, okay, then if I try to go with CB, then once again, if I reach the point D, if you calculate this also, okay, once again, the value will be getting it as 0, because it is also a loop now. You started at a D, you travel to C, then travel to B, then finally come back to the point D. Finally, this is equal to 0. Now, V, start with B, and then we'll try to go ahead with A, D, C. Finally, once again, if you reach to B, then also the value is equal to 0. Okay, I'll try to take the next thing. I start with B, A, D, C. If I calculate this, this is exactly not equal to 0, because it is not a loop. It is not a loop. That's what you need to understand. Okay, so whenever there is a loop means once you start at point and you come back to the same point, and if you add algebraically the sum of all voltages, and if you try to make it as exactly equal to 0, is equal to 0, that's what KVL says. So that is valid for this first two things, whereas the last one I did not consider the loop here na. So this is not exactly equal to 0, hence it is not a loop. Okay, so finally what the KVL is saying, KVL, Kirchoff's voltage law, the algebraic sum of voltage in a loop is exactly equal to 0. The concept here I have explained by taking different individual nodes and their potentials. Now in the next lecture we will try to consider a simple loop having some batteries and resistor combination. Then in that loop we will try to go ahead in applying the KVL and we will try to understand the things. So thank you for giving this opportunity. So this is Dr. Vijaya Babu signing off.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.